In physics, a rigid body of arbitrary shape and mass distribution is called a spinning top or simply a top, if it rotates either about a fixed point of the body or any of its non-fixed point that does not change its position during the rotation. For example, the motion of a flying disc or the front wheel of a bicycle about its center of mass can often be ignored in the first approximation, and the disc or the wheel rotating about its center of mass supposed to be at rest can also be considered as a spinning top. We already saw that the lengths A, B, and C measured along the symmetry axes of the inertia ellipsoid of a rigid body with respect to the instantaneous axis of rotation passing through the point O given by the angles alpha, beta, and gamma, determine the principal moments of inertia IA, IB, and IC of the body with respect to the axis of rotation. The principal moments of inertia of the body with respect to the point O of rotation are generally not the same, and the motion of the body can be very complicated. Therefore, we will only deal with the symmetric top, perhaps the most frequently used spinning top in practice, for which two of the three principal moments of inertia of the body are equal to each other, and the center of mass of the body is on the axis of symmetry. Consequently, the ellipsoid of inertia for a symmetric top with respect to the point O of rotation is a rotational ellipsoid. For example, a homogeneous cylinder or other solid of revolution like the spinning top shown in the first photo is a symmetric top, if the fixed point O is a point on the axis of symmetry of the body. Flat tops also occur in many applications. Their moment of inertia is the largest for the axis of symmetry, that is the principal moment of inertia IC is greater than the principal moment of inertia IA, while in the case of elongated tops IC is less than IA. Spherical tops are normally considered as a class separated from symmetric tops, but they can also be regarded as a special case of symmetric tops, where all three principal moments of inertia are equal. In the case of a force-free top or torque-free top, the net torque with respect to the point O that is produced by the external forces acting on the body is equal to zero. In order for the gravitational force not to exert a torque on the top, the point O must coincide with the center of mass C of the body. This can be accomplished for example by properly adjusting the weight that can be shifted on the rod of the spinning top, or by using the cardan suspension or gimbal system, where a set of two or more pivoting rings called gimbals with intersecting axes allow an inner object to remain level or keep its orientation regardless of the motion and the instantaneous orientation of the outer support. In order to study the motion of a force-free top, let us determine the angular momentum of a spinning top. We already saw that the angular momentum L of a rigid body can be determined by approximating the body with a system of point masses mi, and it can be written as the sum of the cross product of the position vector Ri of the mass element mi with respect to a point O on the axis of rotation, and the momentum pi of the point mass from I equals 1 to the number n of the point masses. The momentum pi of the point mass mi is equal to the mass mi times the velocity vi of the point mass mi, where the velocity vi of the rotating point mass can be written as the cross product of the angular velocity vector omega of the rotating rigid body, and the position vector Ri of the point mass. Because the sum in the right-hand side has the triple cross product of the vectors Ri, omega and Ri, we can apply the vector identity stating that the cross product of the vector A with the cross product of the vectors B and C is equal to the dot product of A and C times B minus the dot product of A and B times C. Then the angular momentum L of the spinning top is given by the sum of the mass mi times the difference between the dot product of Ri with itself times omega and the dot product of Ri and omega times Ri from I equals 1 to n. As a result, we obtain the sum of mi times Ri squared times the vector omega from I equals 1 to n, minus the sum of mi times the dot product of Ri and omega times the vector Ri, from I equals 1 to n. Now we determine the components of the angular momentum L of the rotating body in a Cartesian coordinate system with the origin O, where the coordinates of the position vector Ri are given by xi, yi and zi. The x component of the angular momentum L is equal to the sum of mi times Ri squared times the x component of the vector omega from I equals 1 to n, minus the sum of mi times the quantity of xi times omega x, plus yi times omega y, plus zi times omega z, times xi, from I equals 1 to n. If we gather the terms containing omega x, then we can write the right-hand side as the sum of mi times the difference between Ri squared and xi squared times omega x from I equals 1 to n, minus the sum of mi times the quantity of xi times yi times omega y, plus xi times zi times omega z from I equals 1 to n. By expressing the square of the position vector Ri in the terms of coordinates, we can write the first term as the sum of the mass mi times the square of the y-coordinate of the position vector Ri plus the square of its z-coordinate, times the x-coordinate of the angular velocity vector omega from I equals 1 to n. The second term in the right-hand side then is expressed as minus the sum of the mass mi times the product of the x and y coordinates of the position vector ri, times the y coordinate of the angular velocity vector omega from I equals 1 to n. Finally, the third term in the right-hand side is given by minus the sum of the mass mi times the product of the x and z coordinates of the position vector ri, times the z coordinate of the angular velocity vector omega from I equals 1 to n. If we look at these three terms in the result, we can identify the moment of inertia I sub xx of the body in the first term, the product of inertia I sub xy in the second term, and the product of inertia I sub xz in the third term. Then we state that the x component of the angular momentum L of the spinning top is given by the product of the moment of inertia I sub xx and the x component of the angular velocity omega, plus the product of inertia I sub xy times the y component of the angular velocity omega, plus the product of inertia I sub xz times the z component of the angular velocity omega. This is the general expression for the x-coordinate of the angular momentum vector L of a spinning top written in a Cartesian coordinate system that is not a principal axis system of the rotating body. Obviously, we obtain the same result if we expand the triple cross product of the vectors ri, omega and ri in the coordinate system instead of using the vector identity. The cross product of omega and ri gives a vector with the components zi times omega y minus yi times omega z, xi times omega z minus zi times omega x, and yi times omega x minus xi times omega y. Then the x component of the triple product given by yi times the z component of the cross product of omega and ri, minus zi times the y component of the cross product of omega and ri, can be written as follows. Yi times the difference between yi times omega x and xi times omega y, minus zi times the difference between xi times omega z and zi times omega x. By reordering the terms in the right-hand side we will have the sum of yi squared and zi squared times omega x, minus yi times xi times omega y, minus zi times xi times omega z. If we insert this result in the triple product in the expression of the x component of the angular momentum L, we obtain the same result as the one derived by applying the vector identity. We can repeat the same calculations to derive the y and z components of the angular momentum of a rotating body in a Cartesian coordinate system with the origin at the axis of rotation. Then besides the x component of the L vector, we obtain its y component given by the product of inertia I sub yx times the x component of omega, plus the moment of inertia I sub yy times the y component of omega, plus the product of inertia I sub yz times the z component of omega. Similarly, the z component of the angular momentum L can be written as the product of inertia I sub zx times the x component of omega, plus the product of inertia I sub zy times the y component of omega, plus the moment of inertia I sub zz times the z component of omega. Here we also show all the moments and products of inertia of the body approximated by a system of point masses with respect to the axis of rotation passing through the origin of the coordinate system. By inspecting the structure of the three-component equations of the angular momentum L, we can introduce a matrix notation for the complete set of moments and products of inertia of a rigid body with respect to a point or an axis of rotation. The moment of inertia matrix I with the diagonal elements given by the moments of inertia and the off-diagonal elements given by the products of inertia is a symmetric matrix, as the explicit forms of the matrix elements show, which are constructed from the quadratic sums and the products of the Cartesian coordinates of the point masses approximating the rigid body. Consequently, we can state that the angular momentum L of a rigid body rotating with a given angular velocity omega about a given axis described by the angular velocity vector omega is equal to the product of the moment of inertia matrix I of the rigid body and the angular velocity vector omega. Since the vectors and the matrix in this vector equation are physical quantities, the choice of the coordinate system in which the vector components and the matrix elements are expanded has no role in determining the angular momentum vector from the moment of inertia matrix and the angular velocity vector. Similar to the invariance properties of the dot and cross products of vectors with respect to coordinate transformations, it can be shown that the product of the moment of inertia matrix and the angular velocity vector transforms as a vector under coordinate transformations. If we select another coordinate system and determine the elements of the moment of inertia matrix I and the components of the angular velocity vector omega in the new coordinate system, then the components of the angular momentum L in the new coordinate system are given by the matrix vector product expanded in the new coordinate system. This indicates that the collection of the moments and products of inertia of a rigid body with respect to a given axis of rotation can be interpreted as a linear map on the Euclidean space. That is, the map I defined for a rigid body rotating about a given axis transforms the angular velocity vector omega describing the speed of rotation and the orientation of the axis into the vector of the angular momentum L of the rotating body with respect to the axis. The evaluation of the linear map I at the vector omega is simply defined by the matrix vector multiplication of the matrix I and the vector omega expanded in an arbitrary coordinate system. This linear map is a second-order symmetric tensor called the moment of inertia tensor of a rigid body with respect to an axis of rotation, and the matrix is just the representation of the tensor in a given coordinate system. A different choice of a coordinate system provides a different representation of the moment of inertia tensor of a rigid body with respect to a given axis of rotation. Based on these concepts, the rotational energy, or the kinetic energy of a rotating rigid body with a center of mass at rest can be expressed in the terms of the moment of inertia tensor and the angular velocity vector of the body. We already saw that the sum of the products of the principal moments of inertia of a rigid body rotating about a fixed axis and the square of the components of the angular velocity vector describing the rotation determines the kinetic energy of the body in a principal axis system. We can generalize this result by expressing the kinetic energy of a rotating body by 1/2 times the dot product of the angular momentum L of the body and the angular velocity vector omega. If we substitute the product of the moment of inertia matrix I and the angular velocity vector omega into the angular momentum L, we can write the kinetic energy as 1/2 times the dot product of omega and the product of I and omega. Because the dot product is associated with the matrix vector product, we do not need parentheses in this expression. Hence the kinetic energy is equal to 1/2 times the symmetric quadratic form I of the moment of inertia of the body evaluated at the angular velocity vector omega of the body. That is, the second-order symmetric tensor I maps the Cartesian products of two three-dimensional Euclidean spaces onto the real line, where the mapping of the Cartesian product of the vector omega with itself is defined by the vector omega times the matrix I times the vector omega. We note that tensors are important mathematical objects applied in physics to describe physical quantities. In the beginning of this course we introduced scalars representing a fundamental mathematical description of physical quantities which are determined by one real number and a unit, for example the mass of point-like objects or rigid bodies. In kinematics we also define vectors representing another fundamental mathematical description of physical quantities, which are determined by a magnitude in a given unit and a direction like the velocity of a moving body. They are frequently visualized by arrows in a graphical representation, and the parallelogram rule holds for their addition. Tensors provide the most general mathematical description of physical quantities which involve not only magnitudes and directions but also planes in space associated with the action of tensors interpreted as linear maps between vectors or between vectors and scalars. As in the case of vectors, tensors can also be expanded in some basis constructed from a set of vectors in the Euclidean space. For example, by choosing the coordinate basis of the mutually orthogonal unit vectors EI defining the Cartesian coordinate axes, where the index I runs through the coordinates x, y, and z, we can evaluate the moment of inertia tensor I at the basis vectors, obtaining the matrix elements I sub ij in the given Cartesian coordinate basis. As a result, the basis expansion of the symmetric second-order tensor I can be written as the sum of the matrix elements I sub ij times the tensor product of the basis vectors ei and ej where the indices I and j run through the coordinates x, y, and z, and the basis expansion of the tensor provides the symmetric matrix representation of the tensor which is applied in computations involving the tensor. The basis expansion of vectors and tensors and the formula expressing the angular momentum by the product of the inertia tensor and the angular velocity vector clearly show the following. If the components of the angular momentum L and the angular velocity vector omega are determined in a fixed coordinate system in space, then the components of the moment of inertia tensor depend on time. This is due to the fact that the angular momentum of a force-free top has constant components in a coordinate system at rest, whereas the components of the angular velocity are time-dependent in the rest frame. For the product of the moment of inertia matrix and the angular velocity vector to be constant, the elements of the matrix must depend on time. However, in the principal axis system which rotates with the top spinning about an instantaneous axis, the products of inertia of the body, that is the off-diagonal elements of the moment of inertia matrix, vanish, and the right-hand side of the component equations of the angular momentum L of the body reduces to the terms containing the principal moments of inertia, that is the diagonal elements of the moment of inertia matrix. Namely, the component of the angular momentum L parallel with the principal axis A is equal to the product of the principal moment of inertia IA and the component of the angular velocity omega parallel with the principal axis A. Similarly, we can write that LB is given by IB times omega B for the principal axis B, and LC is equal to IC times omega C for the principal axis C. It follows from this result that the angular momentum and the angular velocity vector of the force-free top have the same direction only if the angular velocity vector points in the direction of any principal axis of inertia of the top. In such a case there is only one non-zero component of the angular momentum and the angular velocity vector in the principal axis system. If the direction of the angular momentum and the instantaneous direction of the angular velocity vector of a force-free top are the same, then the law of conservation of angular momentum stating that the angular momentum of the force-free top is constant, involves that the angular velocity vector of the top is constant as well. Hence the direction of the axis of rotation does not change in time for a force-free top. We conclude that only a principal axis of inertia can be a free axis of rotation. Now we can use these results to describe the motion of a force-free symmetric top qualitatively. By definition, the principal moments of inertia IA and IB are equal for a symmetric top, therefore all the axes passing through the point O in the plane spanned by the principal axes A and B are equivalent. This means that the equations describing the components of the angular momentum L of the top parallel with the principal axes A and B are the same, and we have only two independent equations stating that LA is equal to IA times omega A, and LC is given by IC times omega C. Let us suppose that the angular velocity vector omega of a symmetric top, that is the axis of rotation and the symmetry axis C are in the plane of the figure at a given instant of time. Since the axis A has an arbitrary direction in the OAB plane, we can choose this axis so that it also lies in the plane of the figure. Then we can decompose the angular velocity vector omega of the symmetric top with respect to its principal axes A and C, obtaining the components omega A and omega C parallel with these axes. Now the two equations describing the angular momentum L of the symmetric top show us that the vector L is also in the plane of the figure, which has a decomposition with the components LA and LC. Due to the law of conservation of angular momentum for a force-free symmetric top, its angular momentum L is a constant vector, that is, its position is fixed in the plane of the figure. At the same time, the axis of symmetry C leaves the plane of the figure as it rotates about the angular velocity vector L. Because the direction of the axis of rotation of the force-free symmetric top is instantaneous, the angular velocity vector omega also leaves the plane of the figure. The motion of the axis of rotation given by the angular velocity vector omega and the axis of symmetry C can be studied in simple experiments with spinning symmetric tops. The observations in such experiments demonstrate that both the axis of rotation and the axis of symmetry move on conical surfaces with the same angular velocity about a common axis given by the angular momentum L, which remains constant in space but changes its direction with respect to the body. Consequently, in the motion of a symmetric spinning top, three axes play an essential role. The axis of symmetry C, directly visible from the shape of the top, the instantaneous axis of rotation pointing in the direction of the angular velocity vector omega, and the axis pointing in the direction of the angular momentum L, which is not directly visible. These findings can be summarized as follows. The axis of symmetry of a force-free top and its axis of instantaneous rotation moving with constant angular velocity describe two circular cones about the axis of the angular momentum of the top, which is a constant vector in space so that the three axes always lie in the same plane. This general motion of the force-free top is called nutation, where the conical surface on which the axis of symmetry C moves about the fixed axis defined by the angular momentum L of the spinning top is the cone of nutation. The other conical surface on which the instantaneous axis of rotation moves about the angular momentum vector is known as the space cone. Under special initial conditions, the three axes coincide, that is, the nutation is simplified to a rotation around a free axis. In this case we can talk about a nutation-free spinning top. In addition to the cone of nutation describing the motion of the axis of symmetry and the space cone at rest with respect to the space, we also show the body cone at rest with respect to the top describing the motion of the axis of rotation about the axis of symmetry C of the top. The space cone and the body cone touch each other along the instantaneous axis of rotation defined by the angular velocity vector omega, and we can interpret the motion of the top as the body cone rolling on the space cone. In reality, due to friction at the point O of support, the angular velocity of the nutation and the angles that the axis of symmetry C and the axis of rotation make with the axis of the angular momentum slowly decrease.